Hi everyone, I'm Kien-Tuan at my college, Thu-Trang Nguyen, Sơn Nguyen, and my supervisor, Hieu who all comes from University of Engineering and Technology, Vietnam National University. Today, I'm very grateful to present you about our challenge case which was proposed in the 25th International System and Software Product Line Conference. The challenge case is about the application of fault localization in software product line, also called variability fault localization. So, what is the term variability here? Let me start to explain all about it. In the beginning, I will revise some basic notation in software product line. A software product line, or SPL for short, is a highly configurable system that enables developers to tailor the family of products from reusable software assets. As you can see in the picture located in the right of this slide, it shows an example of SPL system named Elevator, which simulates all the functionalities of an elevator in practical. All the feature status, on or off, are controlled by the options, also known as configurations. This system contains 6 different features: base, width, empty, overloaded, executive floor, and two-thirds full. All the feature status, on or off, are controlled by the options, also known as configurations. So, as you've seen, in SPL, a feature is a basic unit of functionality additional to the base software. When we combine a set of features following a configuration, we then have a complete product, which can be considered as a singleton program. However, because of the configurable option, enable or disable of each feature, if a bug exists in a feature, it is reviewed in only some of composed products. For example, the bug in the elevator system lies in the overloaded feature, but when it is disabled, you will have a product that's completely bug-free. So, it seems like when you re-enable overloaded, the failures will happen. But the answer is, in some scenarios, even when overloaded is on, the bug might not be reviewed because it needs to collaborate with the other features, for example, to test full to expose the failures. So, when this happens, I will elaborate in the following source code example. The code in the right side shows a simplified variability bug in elevator system. The function check elevator capacity is defined to determine if it is needed to block the door and wait for some people to get out until it fits the allowed capacity. So the elevator can close the door and continue to go to the next floor. Looking at the conditions of blocking the door, they're based on 2 measures: the number of persons and the total weight. In this code, you can see that we have 3 features involved in. The feature base check if the number of persons surpass the max capacity of the elevator. If it is, the elevator door will be blocked. Next, about the weight capacity, the feature two-thirds full check if it is exceeded two-thirds max capacity of elevator. And the other overloaded check if it completely exceeds the max weight. And especially, the bug in this example is at line 16, when it needs to check greater than max weight. It accidentally used the equal sign, which is wrong. We need to patch it to the greater or equal sign, which fits the expected behavior. So, start with how the bug will be reviewed through failures. We consider the function in case of the feature two-thirds full is disabled. Over here, We check the person capacity as usual. Assume that it is still fewer than the limit, so it's okay. The block is still false. Next, we directly go to validate the weight capacity. So the problem happens here. Even when the actual weight is much bigger than the expected limit, the door still open and not be blocked due to the wrong comparison with the equal sign. When we test this function, the failures will show up when it runs over this location. Next, how about the behavior of this function if the feature to test rule is enabled? The function is ran and we still see the door is not blocked when check the person capacity. About the weight capacity, in this scenario, we have two conditions to validate. The first one is the current weight does not surpass the 2/3 of the max weight, and the second one, it does not surpass the total max weight. The important thing is that because now the current weight is validated through two levels, and the first if condition will covers the second condition. We can also understand as that if it exceeded the weight limit, it will be bigger than 2/3 of the limit too. So, when the test runs over the 2/3 weight condition, the block will be set to true, and the last condition becomes useless. In consequence, in this case, failures shown in the previous configuration will never happen with this one. With this example, you have seen that even when the bug is visible in the code, it might not reveal its abnormal behavior, and it only showed up in some configurations. The reason is, in SPL, the features usually collaborate or interact with others in the program to build up functionalities. The presence of a feature interaction makes certain statements behave differently from when the interaction is absent. For variability bugs like this case, to localize the buggy statement, we need to find the root cause of the failures in the failing products and identify the relevant features, as well as the interaction among them. About the method to pinpoint the bug in a buggy program. The existing fault localization are not designed for this kind of bugs. These techniques are specialized for finding bugs in a singleton program, correspond to a particular product in SPL system. And when adapted on SPL, we have multiple rank lists for single system, which is failed by variability bugs. The problem here is that developers who use this list cannot determine the right starting point to diagnose the root cause of the system failures. So, that's why we need new adaptation on localizing variability bug. How we use the SPL specialties like the variability of failures and the interaction among the features. The challenge case is raised to encourage researchers and practitioners to propose better solutions for variability for localization. We contribute a dataset including 1,570 buggy versions of 6 SPL systems. It contains extensive test suites, and they are not only the version contain single bug, but also the version contain multiple bugs. Proposed challenge solutions should be evaluated using standard metrics that are widely applied in existing fault localization studies. In the following slides, I will give you a close look to the process to generate the asset in this challenge, especially the benchmark dataset of variability bugs. As constructing a dataset of real variability bugs with corresponding tests is a non-trivial task. Until now, it is hard to find one. Also, some researchers have shown that the performance of fault localization technique on real bugs can be estimated based on their performance on artificial bugs. That motivates us to propose a dataset of artificial variability bugs that are systematically generated. We design a process to generate variability bugs, including three main steps. First, we generate the test suite. Second, we seed the bugs into the system. And the last, we verify the bugs are variability bugs. So, we will come to the first step to see how the test suites are generated. For an SPL system, a set of products of the system is sampled based on a set of valid configurations that the system feature model defined. For each configuration, a product is composed from the implementation of all the enabled features by using the feature house composer. In this step, we will have multiple singleton products. Then several test suites will be generated to capture the original behaviors of these products. Especially, the test output will be recorded and used as the test oracle. In the step 3 and 4, we need to inject a fault into an SPL system. We randomly apply a modification to the original source code of the system by using a mutation operator. We expect the operator will change the original behaviors of several products, produce output that is different from the recorded output in the last step, and the test suite generated in step 1 will be able to capture them. Besides, we want to note that we only create mutants at the statement level and do not apply any operator which delete a whole code statement. In the final step, we need to verify each generated bug is a variability bug and caught by the test. A product considered as a passing product if it passes all the tests, and a product which fails at least one test is so-called a failing product. The bug is considered as a variability bug if it causes the failures in certain products only. After this step, we will have a complete SPL system contains single bug with test suite. We also extend the process to inject multiple bugs into the SPL system. The design is similar, except in step 3, we create multiple modifications in the source code. In the experiment, we apply the process on 6 SPL systems collected from the SPL2Go website. The table is showing basic results after we create the variability bugs. As you see, we generated a total 1,570 buggy versions of 6 subject systems. The bug contained the modification related to some mutation operator group, such as arithmetic, conditional, or relational. The bugs are often injected to the conditional or assignment code statements. Besides, in the final column, you can see the number of involving features that related to the bugs. As I know, performance of localization techniques might influence by the number of features which must be actually enabled or disabled to review the bugs. And in our dataset, the number of involving features is from 1 to 25, and in about 76% of the cases are less than 7. So, how about the participant can evaluate their solution on the benchmark dataset has been mentioned. Proposed localization method need to produce a ranked list of suspicious statements. We show here 4 standard metrics. The first one is rank. The low rank developer will find the bug faster on the list. The second is exam, which presents the percentage of statements that must be examined until the first 40 statement is reached. The third, recall at top end, shows the number of cases that at least one bug was found after examining an statement in the ranked list. And the last one, the proportion of bugs localized PBL, we apply on localizing multiple bug cases. Present proportion of the bugs which are detected after examining a certain number of statements in the system. With this metric, we apply a simple localization technique and show the baseline result in our article. Let me summarize some figures of the result in this slide. We construct a baseline method in several experiments with the naive adaptation of spectrum-based for localization, also known as SPFL. Especially, we consider the whole SPL system as a non-configurable code. The suspiciousness score of a statement is measured based on the test counted from all the products. In summary, for single bug, 71 bugs and about 21% of the total bugs are correctly ranked at top 1. And it increases when more statements in the ranked list are examined. About 82% of the bugs are ranked at top 5 positions. With the multiple bug cases, about 17% and 92% of the cases have at least one bug ranked at top 1 and top 5 positions. On average, using PBL metrics, only 7% of the bugs can be found after examining the first statement. So, I gave a short presentation about the challenge case variability for localization. I also show how we constructed the benchmark dataset of 1,570 buggy versions of 6 SPL systems. And by providing several standard metrics, we able to measure the for localization technique performance. We hope that the contribution encouraged the researcher to propose better solution for the challenge case. Thank you.